Here we're going to look at the global circulation of air. We're going to be studying how monsoons, which are pretty much large-scale land and sea breezes, are driven by a pressure gradient force. So we're going to start making sense of this map in terms of the directions of the winds that we view and that are named, and from these convection cells that are also named. We will then correspond that to, well, let's just say features of the Earth, whether we're talking about a tropical region along the equator or a desert region at different known latitudes, just based on what the winds are doing, what these convection cells are doing. So by looking at this map or this picture of the Earth right here in these global circulation belts, we can actually draw a lot of conclusions about what's taking place on a planetary scale. So the underlying cause of atmospheric circulation, right, these convection cells, are simply the unequal surface heating. Different objects heat up a little differently. Land heats up differently than water. Different albedos, or lightness and darkness, change the heating ability. These different the surfaces are going to be driving winds. On the rotating Earth, there are three pairs of atmospheric cells that redistribute the heat. From 0 to 30, we call them Hadley cells. From 30 to 60, we call them Ferrel cell. And from 60 to 90, we call them polar cells. This is an idealized global circulation, and we're going to start off with what we call the equatorial low pressure zone. Here along the equator, it's denoted here in red, sometimes referred to as the doldrums. This is where we have rising air, we have abundant precipitation. This low pressure is very consistent with the low pressures we studied in the past. The air is going to rise, it's going to be condensing due to adiabatic cooling, and it's going to be precipitating out whatever excess moisture. So we'll find that along the equatorial low, we're actually going to be able to find the vast number of tropical rainforests that exist on Earth. So looking here, if I move on, so let's move up 30 degrees. I get to the subtropical high pressure zone. This is where air is subsiding, right? Moving downward. It's stable. It's very dry. This is near 30 degree latitude. This is the location of great deserts. So desert regions of the Earth occur in and around this area. Air traveling equatorialward from the subtropical high produced the trade winds. Well, let's look at that for a second. If this is high pressure and the equator or the equatorial low, I'm going to be getting a pressure gradient force from high to low. But remember, if I'm facing the equator, if I'm standing here and I'm facing the equator and it moves in a straight line, the Coriolis is then going to deflect it to the right. So these curved lines are simply the deflection. I go from a high subtropical high pressure zone. As it blows towards the equatorial low, it's going to be deflected to the right due to the Coriolis. So that's what these lines are here. And in the southern hemisphere, it's going to be deflected to the left due to the Coriolis. So the trade winds are simply traveling from the subtropical high pressure, to the equatorial low. So we can look at this map here where I have my equatorial low, I have my subtropical high. This is driving my trade winds. Here we're looking at roughly 30 degrees north and 30 degrees south. We can find that deserts, these are the result of the warm air, right? Warming air that's compressing. It's descending at roughly 30 degree latitudes, right? 30 degrees north, 30 degrees south, both north and south of the equator. The dark line above, this is my equator, just to kind of give you a little reference here. Just show that deserts are situated at roughly equal distances from the equator. And this is precisely where global wind belts associated with high pressure are located. So the planet, on a large scale, reflects the conditions of these global wind belts. So here I can look at my subpolar low pressure zone. So here's my subpolar low pressure zone. These are warm and cool winds. This is where they interact. Here's my warm winds. Here's my cool winds. This is where we have polar fronts, an area of storms. This is simply where different types of weather systems, let's just say, evolve. So here I have a polar high pressure zone. These are going to be at my poles. These are cold subsiding air. Notice that this is a convection cell. It's traveling downward at this location. Air spreads equatorward and produces polar easterly winds. Polar easterlies then collide with westerlies along this polar front, and this is my polar front here. So I'm going to go look here at the westerlies. Let's make sure we understand that we have the subtropical high It's moving toward my subpolar low. If I travel from high to low, this is my pressure gradient force. And notice, if I consider Coriolis, it's going to deflect it to the right. So the westerlies are simply traveling from the subtropical high to my subpolar low, high to low, deflected to the right, and this generates my westerlies. So the influence of continents. So we can now apply what we've been looking at here to seasonal temperature differences that disrupt both global pressure patterns and global wind patterns. This influence is most obvious in the northern hemisphere, right? We have more land, much more land in the northern hemisphere than the southern hemisphere. And these are what generate monsoons. Monsoons are seasonal changes in wind direction. So I'm going to look at this. This is my intertropical convergence zone, or my ITCZ, and this is a low pressure region, right? I have air that's, let's just say it's coming together. It's converging is the word I was struggling to get there. It's converging, right? It's going to rise. Rising air is a low pressure system. So low pressure here. If I look at my next slide, I'll move these back and forth just so you can kind of get the difference between them. Here my ITCZ, my intertropical convergence zone, has moved over land. Notice the air that's blowing onto land is warm, moist air that comes from the bodies of water around it. So air that's warm and moist is going to rise and cool adiabatically, and with it's going to bring tremendous amounts of rainfall. So if I dance these two back and forth for a second, let's see if I can do this. Observe the ITCZ different seasons. During the northern hemisphere winter, right, during January, let's just say it's not really affecting, it's not driving that much moisture and precipitation onto land. So the ITCZ is much further south, right? It's actually reflecting the isotherms that we've been able to study in this unit. But if I look at what's taking place in the summer, that ITCZ, the intertropical convergence zone, is driven onto land. Now notice the high pressure is out here. It's driving this warm, moist air onto land. It's getting tremendous rainfall. These are the monsoons. The monsoons are simply the result of where the high and low pressure systems are located. Here's another low pressure system. Whereas in the winter months, I've got my Siberian high on land. It's pushing air. This is all land breeze, right? If I'm in this part of Africa or this part of India or this part of Asia, I've got this high pressure. These are all land breezes. These are very dry. Yet in the summer, right? So winter are land breezes. In the summer, these are sea breezes, and with them they pack some serious moisture. So when I compare these two maps here, we're looking at monsoons. These occur over continents. These are during the warm months. Air flows onto land, right? This is what we defined as a sea breeze. They're warm, moist air from the ocean. In the winter months, air flows off the land. These are what we call land breezes, and it's dry continental air. It just doesn't have the ingredients. Now, we've already looked at this. I just want to reiterate. I've got a low pressure system, an equatorial low. I then have a subtropical high. I then have a polar low. And then I have an extreme polar high. And these are the associations of both north and south. Low, high, low, high. Where I have low pressure, I have rainforest. At the equator, I have tropical rainforest. At roughly 60 degrees-ish, plus or minus, I have what we call temperate rainforest, right? There's a lot more land in the northern hemisphere than the southern, so I don't get the same temperate rainforest in the southern. But there's definitely temperate rainforest in the northern hemisphere. And then I get a desert where I get these high pressure systems where air is descending, it's compressing, it's heating adiabatically, it's going to be warm, dry air. And these are where I get my desert regions, and that's what this picture is illustrating here. I also want to make sure you realize that where I get descending air at the poles, both the North and the South Pole, those are huge deserts. They're tremendously dry, they're just cold. So not all deserts reflect warm, dry air. They just reflect dry air. And last but not least, last couple here, the zone of the westerlies, they're very complex. Airflow is interrupted by cyclones. That's what we've defined as these counterclockwise moving low pressure systems. Cells move from west to east in the northern hemisphere. These are generating both anticyclonic and cyclonic flows. And the passive cyclones and anticyclones are associated with upper level airflow, or the jet stream. So the westerlies are driving our weather from the west to the east. And there you have large